encrypt each of the output addresses and send them to a user in such a way that when they're decrypted, it is impossible to know who that address came from. Now the downside of this is that it doesn't scale very well. For 3 players, it's actually quite easy, but for n players, it only scales to, well, it takes the square. We need n square encryption. The encryptions where n is the number of users in there, so that's quite expensive and prohibitively so at this point. Now there's a second approach that was proposed by Edward Z. Yang in 2012, and he uses secure multi-party sorting. In this case, it's a general multi-party protocol that takes all the addresses on the right here, and that takes them as private inputs and outputs a list of the sorted addresses in alphanumeric terms. Now, the fact that they're sorted is strictly useless, but what is interesting here is that it produces all the addresses without revealing who inputted what. And at this point, Alice can just send to the first one, Bob to the second one, and Charlie to the third. Again, we have problems with feasibility of this managed. We have problems with feasibility because it requires quite a certain number of comparisons and a certain number of rounds. And the big downside here is that comparing large strings, as Bitcoin addresses are, rather large strings for these, and it's hard and it's expensive. So really no implementation of this at this point. Now, there is the second approach that I'm pioneering here that uses a circuit of very small and simple transaction. Now, this transaction is also inspired by Randy Rosenfeld, and I call it a two-party anonymization gate. The idea is the following. We have only 2 players here. We have Alice and Bob, and together they will decide, all right, we're going to do some mixing. So they each produce an input and an output address. Well, the input address that we had, but anyways. And so they produce an output address, and they can actually share it with one another in this case. So this is different from the previous case. And they're just going to, once this is established, they just flip a coin. And that coin is going to decide, do they send, does Alice send to Alice and Bob send to Bob? Or does Alice send to Bob and Bob send to and Bob send to Alice? Now, of course, Bob or Alice can't cheat in this because this is one atomic transaction, so Alice can't wait to have her secret funds and not send the funds to Bob. That's not how it works. Now you're going to tell me, well, this is entirely useless because, of course, Alice knows what Bob's output address is. It's just the one that isn't hers, and vice versa, and you're right. But what's important here is that these players have gained a certain amount of anonymity with respect to other players watching the blockchain, because they do not, these users do not know the results of the coin flip. They do not know if which address on the right belongs to Alice and which address belongs to Bob. So this is the idea. You build circuits out of these very simple and not very anonymizing transactions to get a better result. And what we want to have here is to maximize the resulting entropy in complicated terms, but the idea really is to minimize the probability that an adversary could be looking at these transactions, looking at the blockchain, and guessing the correspondence between the addresses. Now we have to be careful here because, as in all mixing protocols, the adversary can actually be part of the mixing protocol and either be malicious or active, or just look at the results of the transactions. So really, this mean entropy here that we're trying to calculate depends on the number of adversaries, on the position of these adversaries in the circuit, and on the result of the coin flips. So there's 3 circuits that I'm studying at the moment. The first one is really quite simple. There's end users that get together and they just say, all right, we're going to want to do some mixing together, so just every round pick someone at random and do 2-party anonymization. So that's what the players do. And after a certain number of rounds, they stop and say, okay, so what have we gained? Well, chances are you ended up mixing with a few people, so somebody looking at the blockchain will have a little harder time finding out really who you are. But the downside of this approach is that you can be unlucky and and you know, just mix with a few people, always the same people, and then it's really, you've gained anything. So to answer to this problem, that is using a butterfly network, which is a network that has the interesting property that at the end of the execution, Alice could be anywhere. So it's a log depth circuit, which is optimal for what we want here. And it has that set of property that if an adversary isn't looking, Alice could be anywhere at the end of the protocol. And the downside of this is that all permutation of inputs are not possible, which means that if an adversary is included in the protocol, that adversary might actually gain a lot of information as to where Alice might be at the end. And so the final circuit I'm looking at right now is essentially two butterfly circuits pasted together, and it's called the Venice network, and it has this interesting possibility, interesting fact that it can do all the possible permutations. So this is, I think, the most complicated network we want to do, because otherwise it's going to become too expensive. So the depth here is 2 log n minus 1, so a little more expensive than the butterfly network in this case. So if we look at the two approaches here, we have on the left the blueprint approach, and on the right the circuit transactions approach. The blueprint approach is hard to do. It requires a certain number of CPU cycles, just because doing multivariate calculus in the general case is quite expensive. And so it's computationally hard. Also, it is quite prone to denial of source stacks. The idea is that a person that does not want it to work can go through the entire protocol, and at the end, when it comes to time to sign here, it can just refuse to sign. The transaction isn't signed, it's going nowhere, nobody will accept it, so the entire protocol has to fail at this point. Of course, no one is lost, but the service is denied. Whereas for the circuit transaction, if there's just one person that's not doing the transaction correctly, you kick them out of the network, and that'll be it for now. Now, on the other side, the transaction blueprint only has one transaction, so it's quick to confirm, it's easy on the network, and the transaction cost is low. It's actually particularly low, even compared to standard centralized mixers. Whereas for the circuit transaction, it's quite the opposite. Large numbers of transactions means that you're going to have a higher cost, higher burden on the network, and it takes quite a bit of time before every transaction is confirmed. And with those two in mind, there is a third approach that I call the hybrid approach. That's really a mix of this typical centralized mixer and the blueprint approach. And it works in the following way. You just imagine the centralized mixer you had at the beginning, but instead of giving your coins to the mixer, you ask the mixer to produce a secure permutation, as actually did in any case, and then propose the transaction blueprint. If the transaction blueprint is acceptable, everybody signs it, and it's sent to the network. So the good side of this is that the trusted third party can't run the money, because the mixer never actually owns the money. And this is quite easy to implement, I think, because it really doesn't take all that much calculation to do it. Actually, not at all. And the downside, of course, is that no anonymity is gained with respect to that trusted third party. Now, this could be mitigated by chaining together those types of transactions with different mixers that you would assume are not all colluding together. So the end result would be with a very high probability of gaining anonymity there. Which brings us to the conclusion. So what's next, really? Also looking at new ways to create some blueprints. I'm really interested in having some feedback from the community there. Still working on the analysis of anonymizing circuits, which take us a certain amount of time to completely understand how the circuits work and what's the result. And what I'd be really interested to see in the future would be a real-world implementation, even if it's just a hybrid approach. So just as closing thoughts, I think that very strong anonymity is preferable to no anonymity at all. But I think we really have to have a discussion as a community about how we're going to deal with, how we would deal with such a very strong amount of anonymity. Thank you.